All righty, good afternoon. Today we will continue our discussion of radicals and come very close to finishing up if we don't actually finish it up today. Where we were last time was talking about this free radical halogenation reaction, which I demonstrated for you last time. We had methyl cyclohexane, reacted that with bromine. Nothing happened in the dark, but if we added light, a reaction occurred in which a CH bond was replaced by bromine, and we also ended up with a molecule of HBr. We were working out the mechanism for this process and had figured out that the mechanism is 3 steps. It starts with the bromine-bromine bond breaking in a homolytic manner. Each of the 2 bromines gets 1 of the electrons from the bond. That gives us a bromine radical, which has an open octet and an unpaired electron. We talked about how radicals behave, what are their anxieties, so to speak. Addition to pi bonds, atom transfer, or radical combination were our 3 radical fates. The only one that's going to operate here, the only thing it can do is atom transfer. It looked like it was going to work on this hydrogen because that's the one that's replaced in the product. So the bromine atom will steal the hydrogen along with 1 of the electrons of the CH bond. That's going to make a new hydrogen-bromine bond. And then the other the other electron becomes property of that carbon. That gives us a new radical and the molecule of HBr. A satisfying step in our mechanism because it gives us one of our 2 products, and it also operates on the carbon that we want to operate on the product, but the only reason that we did it there initially was because, in fact, that's where it is in the product. So the question became, why here? Well, in any mechanism step, we've said that if you have a choice of doing different things, we generally tend to do the things which are energetically more favorable that lead to more stable products. In other words, why is this the most stable radical? So we talked about radical stability, degree of substitution and resonance and so forth, and came to the conclusion that this hydrogen was abstracted, was taken away because it leads to the tertiary radical. The only other radical possibilities that we could get would be primary by taking away 1 of the methyl hydrogens, secondary by taking away 1 of the methylene hydrogens, or if we take the entire methyl group away, we would also end up with a secondary radical. So that is why that happens. Now we were in a position to finish up, and so we said that the mechanism finishes up by an atom transfer, or an atom theft, whatever you'd like to call it, where this carbon radical takes a bromine from Br2, and that's going to make our product as well as another bromine radical. We talked about taking bromine from HBr. Not as easy to do because that bond is stronger than Br bond. We talked about having this radical react with bromine radical. Thermodynamically very favorable. It forms a bond, pairs 2 electrons, fills 2 open octets. But it doesn't happen to any great extent because we're asking things which are present in low concentration to find each other, and that's difficult to do. And that was where we left last time, and I left you with something to think about. I said this, while it finishes the mechanism, it gets us to our right product, it creates a little bit of a problem. Anybody know what that problem is? Look closely. Anybody have any idea what the problem is? Camera guy, can you zoom in on that? Anybody know what the problem is? Resonance, thank you. Get an A for effort, but we don't grade effort here. Right, so this is a radical. Radicals generally are reactive species. They are, for the most part, with the exception of the one you're breathing, oxygen, radicals are pretty reactive things. For the most part, they're not the kind of things we can put in bottles. They're the kind of things that likes to continue to react. So you ask yourself, I've made bromine radical. What do radicals like to do? They like to add pi bonds, they like to do atom transfer, and they like to do radical combinations. So given what's present in the mechanism, what are they going to do? There's no pi bond to add to. We've talked about radical combination being an unlikely event because of concentration issues. So what's left over? Atom transfer. what atom should we take? Let's have this bromine radical. Take another hydrogen. Okay, that gets rid of the bromine radical, but, oh gosh darn it, it makes methyl cyclohexoradical. Okay, methyl cyclohexoradical reacts with bromine to make more product. That's good. And another bromine atom. So this bromine atom turns around, takes another hydrogen, etc., etc., etc. It keeps going and going and going. It's like the rabbit. You have to blur that out because I'm doing the trademark thing, right? It's the rabbit. Right? It keeps going and going and going and going. In other words, this mechanism has two steps in it that keep cycling through until something stops it. Something consumes radicals, something consumes methyl cyclohexane, it runs out, whatever. A process which has one or more mechanism steps that repeat indefinitely is called a chain reaction. Have we run across any other reactions in which one or more mechanism steps repeat indefinitely? Yeah, any process which is catalyzed works that way. If you regenerate the catalyst at the end and it goes back through another cycle, those are technically chain reactions. We usually don't call them chain reactions. The term chain reaction is usually used just for radical processes. Now, what that means is once I get this thing started, it keeps going and going and going. In principle, I could have taken this reaction, just shined the light on it for a fraction of a second, and it should have gone and consumed everything. Well, the problem is these chains, these radical chains, don't propagate, don't keep going forever. Eventually, radicals get used up, the reactants get used up, etc., which in some ways is good because there are certain radical processes we're going to talk about later that if they never stopped, the world would be in big trouble. All right, so when we're talking about a radical mechanism, we can identify the radical involved steps in one of three categories. There are either categories in which radicals are made, transferred to the next generation, or consumed. So these steps, these chain steps is what we'll call them, come in three flavors. There's initiation, and an initiation step is where we have no radicals, and we produce radicals. And those radicals can go on and make chains. So in other words, chains are initiated. So in our mechanism over here, this step in which the bromine-bromine bond is broken, that is an initiation step. I'll call it I. Then we have steps in which the chain, the radical, so to speak, is passed from one generation to the next. We call these propagation steps. And propagation steps are where we start with a radical, or one or more radicals, and we end up with new radicals. I suppose I should put that in parentheses as well. So any step where we start with radicals, it produces radicals. That would be a propagation. So the step where the bromine atom takes a hydrogen away from methyl cyclohexane, that is a propagation step. We start with a radical. We end up with a radical. The last step in the mechanism that we wrote is a propagation step. We start with the methyl cyclohexyl radical. We end up with the bromine radical. Now, the third possibility, since we went from no radicals to radicals, radicals to new radicals, so the other possibility would be going from radicals to no radicals. And when this happens, the chain can't propagate anymore. The chain is ended, so we call this a termination step. Now, the mechanism we've written up here has no termination steps formally included in it. We can write one. Let's say two bromine radicals come together to make Br2. That would be a termination step. Or a methyl cyclohexyl radical finds a bromine radical and makes product. And that's also a termination step. These don't happen very often, maybe one time out of 1,000 or one time out of 1,000,000 through the cycle, because radicals are generally present in low concentration and their probability of finding each other is pretty small. All right, so we can differentiate these, initiation, propagation, and termination, differentiate those from the radical fates that we talked about. Now, we talked about add to a pi bond, atom transfer, radical combination. The radical fates say if you have a radical, what mechanism steps can it undergo? These simply say in a chain reaction, we can categorize every single step within the mechanism, regardless of what the radicals are, how they behave, as one of these kinds of things. So most of your radical mechanisms are going to have an initiation step, then a bunch of propagation steps. We don't write termination steps as part of the generic mechanism because they don't happen all that often. We know these are chain processes, and we want our mechanism to reflect that. Now here we talked about bromination. And you know, having other halogens in molecules are important. So can we introduce other halogens in the same way? So in other words, if I took methyl cyclohexane and reacted it with, let's say, chlorine and HNu or heat, either one of those will work. Does the process work the same way? Mechanistically, it will look exactly the same. Replace Br dot with Cl dot, and you have the same mechanism. Will you get chloromethylcyclohexane? The answer is yes, but you get other stuff as well. Other chlorine present elsewhere in the molecule. Now, the difference here is that this bromination reaction we've talked about is pretty selective. You get almost exclusive bromination at the tertiary bromide because the bromine radical being less reactive is more selective. It is less desperate and therefore a little more fussy. The chlorine radical that you make here, on the other hand, is more aggressive, and so it's less selective. So you get a lesser domination of this guy. You begin to get products that look like a statistical distribution of where the chlorine can go. All right, so what about iodine? Can I put iodine on? Iodine, what happens if I do iodine, HNu, or heat? Well, what happens in this case is kind of the opposite. And we said chlorine's really aggressive, bromine's a little less aggressive, so what would we think about iodine? Relative to bromine, more or less aggressive? Less aggressive. And it is so non-aggressive that nothing happens. Now, I should say we don't get any iodo product. Something happens, the iodine comes apart. The iodine-iodine bond's very weak. As a matter of fact, if you have a bottle of iodine sitting on your shelf, every chemistry geek should, the iodine's breaking apart, coming back together, breaking apart, coming back together. The bond's that weak. But that's not the issue here. The issue here is carbon-iodine bonds are weaker than other things, and this is just not a thermodynamically desirable process. It's not thermodynamically spontaneous, and the bond energies are such that it just doesn't move forward. So iodine doesn't do anything. All right? What about the opposite end of the spectrum? What about fluorine? Iodine is so non-aggressive as to not react. Bromine reacts, but it's selective. Chlorine reacts not so selectively. What do you think about fluorine? What do you think? If the guy down here, iodine, is unreactive, bromine, a little more reactive and selective. Chlorine is even more reactive and a little less selective. Fluorine, see, I'm following the periodic table. Fluorine will be very aggressive. What's going to happen is you will get fluorine in your molecule. Now, the line out of the middle means we're not specifying where it is. It goes somewhere. It goes pretty much anywhere it likes. It doesn't really care so much about tertiary versus secondary. Because F dot is so reactive, it is very not fussy. It'll take pretty much anything. The N means you're not going to control the number of fluorines that go there. With bromine and chlorine, you can begin to control that. But the fluorine just goes on so quickly, it's hard to stop it at just one. I guess that sounds like a potato chip commercial. Right? We can't stop it at just one. So not only is there no selectivity, you can't, as to where it goes, it's hard to control how many go on there. As a matter of fact, you probably end up replacing all of the hydrogens. The other issue is carbon-fluorine bonds are pretty strong. You end up releasing energy as this reaction goes on. All right, so this energy is produced. What happens when you start feeding energy into the reaction? Heat. This goes faster. So the reaction that makes the energy goes faster and makes even more energy, which makes the reaction go even faster, very difficult to control. So sometimes we call the product of this K-boom because it may just explode. Now, it's nice to have fluorine in molecules because they do lots of things like make Teflon pans. But as it turns out, putting fluorine in this way is generally not very useful. For control reasons are part of it, but also because this stuff. This is about the nastiest element in the entire periodic table. More people died trying to isolate fluorine for the first time than for any other element on the periodic table. Like at least 10 people died until somebody finally figured out how to do it. Same guy, by the way, who invented artificial diamonds. So this will go through lots of things. Glass, for example, your hands, all sorts of nasty things. So this process, not all that important, unless you want to replace every atom with fluorine. Also hard to control in the reaction. Iodination, not useful. Chlorination, useful if you don't mind mixtures or if all the positions are the same, right? If you're chlorinating methane, you know, who cares where the first chlorine goes? That doesn't matter. Bromination, though, that's pretty selective. We can control that. All right, so we're done talking about that free radical halogenation, and now I have to tell you that sometime in the near history of this course, a few lectures ago, I lied to you. I didn't lie. I didn't tell you the whole truth. So I guess I was behaving like a politician. We need to talk a little bit more about that. So I want to talk about HBr and alkenes again. When we talked about the addition of HBr to an alkene like propene, the HBr adds to the alkene's the nucleophile, the HBr is the electrophile, and the addition occurs in a way that puts the halogen on the more substituted carbon, the hydrogen on the less substituted carbon, because that process goes through the more stable carbocation. It obeys Markovnikov's rule. It turns out in the early days, especially when people like Markovnikov were studying this reaction, it didn't always behave. There were times that you could do exactly the same thing, but you would end up with anti-Markovnikov products. Now let me put this in perspective. Bless you. That's not the perspective I was looking for. Imagine you go into the kitchen and you say, today I'm going to make what should we make? A sandwich? What kind of sandwich? We need to be more specific.
Bologna.
A bologna sandwich. Good undergraduate. Cheap white bread, cheap bologna. Mayo or not?
Yes.
Mayo? Oh, you're living the high life. 2 slices of bread, or are we saving money this week? We're saving money. So 1 slice of bread, 1 slice of bologna, but mayo, fold it over. All right. So you go into the kitchen to make a bologna sandwich. And you've made a bologna sandwich how many times before? Probably a lot, right? You go into the kitchen, you make the bologna sandwich, and when you're done, you have pasta, as somebody said. I tried to make a bologna sandwich, and I got pasta. This is making the bologna sandwich, and this is getting pasta. You're going, what's going on here? People didn't understand. So in the 1930s, 2 guys named Karash and, I'm glad you mentioned Mayo, because one of the guys' names happens to be Mayo. Karash and Mayo were studying this reaction, and they figured out what was going on. Now, not so much did they figure out what was going on. It was what they basically proved that was so important here. Karash and Mayo figured out that if your reactants are pure, freshly purified propene, freshly purified HBr, your glassware is scrupulously clean, etc., etc., Markovnikov's rule is followed every time. But if you've got some impurity in here, then, depending upon the nature of the impurity, it may or may not follow Markovnikov's rule. They discovered the impurities that would cause this thing to shift from Markovnikov to anti-Markovnikov were peroxides of some sort. So things, let me draw that out a little differently. We're talking about things with oxygen-oxygen bonds in them. And they got to the point where they could take this reaction and make everything really pure and deliberately add peroxide and then make it go anti-Markovnikov. So they understood that peroxides were causing this. And they also found out where the peroxides were coming from. The peroxides were coming from things like propene being too old, reacting with oxygen in the air, and so forth. That's where these kind of things can come from. All right, so let's talk about the mechanism of this process, and in that we can talk about what Karash and Mayo did that was kind of really much more important. Now, first of all, Karash and Mayo figured out that this was a radical process, and they did it by adding things that were known to inhibit the formation or propagation of radical chains. So we're going to take it for faith that they knew it was a radical process. But let's figure out what the mechanism might be. Well, the mechanism is not going to start with the reaction of the alkene with HBr, because alkene plus HBr goes through the carbocation mechanism Markovnikov addition. So that cannot be how the mechanism starts. That leaves peroxide. All right, let's talk about the peroxide. What does the peroxide do? Now, we might frequently use, let's say, hydrogen peroxide. I'm just going to use that as an example here. But it can be other things. What might this do? Remember, it's a radical mechanism. So if we're going to have a radical mechanism, we need to get it started. How do we start a radical mechanism? We need some sort of initiation step. That doesn't mean we, put a blindfold on it and spank it. That's a different kind of initiation. Maybe radicals do that. I don't know. But we need to break this bond, like so. We're going to make two hydroxyl radicals. Now, you might be thinking, what in the world causes it to do this? Well, an oxygen-oxygen bond, like a bromine-bromine bond, is relatively weak. It can come apart pretty easily. And in this case, generally it's heat that does it, but only just the temperature of the surroundings, the ambient temperature, is good enough to do it. How many of you have ever had hydrogen peroxide in your medicine cabinet? Did you notice it has an expiration date on it? Because this is exactly what it's slowly doing all by itself. It's slowly coming apart. So that makes two hydroxyl radicals. Now, why does it do it? Why is that bond weak? What happens when you put that many lone pairs next to each other? There's repulsion. Think about how that compares with the Br2 case. Both the bromines have lone pairs. You put a lot of lone pairs together, there's repulsion. That tends to weaken those bonds. All right, so that gives us a hydroxyl radical. That's fine. What are we going to do next? We initiated, now we need to propagate. And we need to propagate it in a way that the bromine and the hydrogen are going to add. Now, when we do the addition to the whatever the radical is that's going to add to the pi bond, we can't add it in a way that makes the less stable intermediate. In other words, when we do the reaction with this alkene, and it goes on to put whatever we're going to have attached, we're going to put the radical there. We don't want to put the radical there. That's primary. We want to put the radical secondary. So whatever adds to the alkene is going to do it to make the more stable radical. What does that mean we have to add? There's our product. What has to go in first? What makes the more stable secondary radical and goes here? That's the bromine. So we need to put a bromine there. But we can't add bromine as HBr. It doesn't add that way. So we need to do something else to the bromine, and that's this. Oops, got that backwards. We're going to use the hydroxyl radical to steal the hydrogen, to abstract the hydrogen from HBr. That's going to make a molecule of water, and it's going to make a bromine radical. That's step driven by converting a weaker HBr bond into a stronger OH bond. There's our bromine radical, which can now add to the alkene. One electron from the bromine, one electron from the pi bond. That makes the new carbon-bromine bond. The other electron goes to the carbon. There's our new bromine. So we're still adding to the alkene in a way that makes the more stable intermediate, just like if we were making a carbocation, but here it's a radical. And then what are we going to do to finish up. We're not going to do a termination. We don't do terminations in radicals. We need a propagation that's going to give us this product. Or excuse me, it's going to give us this product. What do I need to do? What's missing? A hydrogen, right? What should I take the hydrogen from? Look at all the stuff that's present in the reaction. Something that might cycle through. Water is a possibility. Turns out the OH bond that we would take from the water is stronger than another bond that we can take hydrogen from, HBr. So if we take the H from HBr, there's the hydrogen, there's the bromine, we make bromine dot, and what does that bromine dot, that bromine radical do? Adds to another alkene, which makes another carbon radical, which abstracts hydrogen from another HBr, which makes another product and another bromine radical, and so on and so forth. So it's another initiation, propagation kind of chain mechanism. Now what Karash and Mayo did, however, that was such a big deal here, was they implicated these things. Not, the bromine isn't the issue. It's this, radicals on carbon. The idea that free radicals could exist before then had been proposed, and people had actually talked about them in certain cases. But carbon, no, it's verboten. We can't do that. It would never happen. But Karash and Mayo said, no, it does, and we have proof. So that kind of opened up a whole new way of thinking, a whole new group of kind of mechanisms to talk about. Now, I want to point out here that what we've seen is an anti-Markovnikov addition of HBr. There's the anti-Markovnikov addition to an alkene. We've seen a bunch of alkene addition reactions, but of the ones that we could describe as Markovnikov or anti-Markovnikov, only 2 have been anti-Markovnikov. And I'm telling you that because it's a way to organize information. If you're unsure, think it's probably Markovnikov, but there are exceptions. 2 exceptions. Here's one of them. Addition of HBr in the presence of a peroxide. And what was the other one? Nobel Prize, H.C. Brown, 1979, shared with Georg Wittig. That probably doesn't mean anything. Anybody have their cell phone out? Go to Wikipedia real quick. Hydroboration oxidation. That's the other one, which is anti-Markovnikov. This changing of the reaction regiochemistry from Markovnikov to anti-Markovnikov in the presence of peroxides is called the peroxide effect. And it sounds really useful. Wouldn't it be cool to take any reaction and just dribble in some peroxide and make it go the other way? It turns out it doesn't work that way. It only works for HBr. HBr plus alkenes or alkynes, either one. That's the only things it works on. It doesn't work on H3O+, it doesn't work on HCl, it doesn't work on anything else, just this. And that has to do with the nature of the bond energies that are involved. All right. Now what I want to do at this point is we're going to switch to our lecture supplement because I want to talk about some miscellaneous radical processes. And in these miscellaneous processes, I don't want to focus so much on introducing lots of new reactions or thinking about all the mechanistic details, but rather most of these are real-world kind of things, and I want you to think about them in terms of some of the kinds of stuff we've talked about. You know, what might the mechanisms be, etc. All right, so the first one I want to talk about is oxygen, O2. Oxygen is a problem because it is a radical. Actually, it's a diradical. Now, when you think about the structure of molecular oxygen, take a deep breath and think about it. You might, okay, this is what we're going to draw. If you work out all the electrons and fill up the electrons according to the usual rules you use for Lewis structures, you would construct an oxygen-oxygen double bond. But this is one time of several that the traditional Lewis structure rules get it wrong. Quantum mechanics gets it right. Oxygen is actually a diradical. So there's one unpaired electron in each oxygen and not a pi bond. Now the reason for that is, as you're putting the electrons into the orbitals, molecular orbitals, and you use the same rules, Aufbau principle, Pauli exclusion, all Hund's rule, all that other kind of stuff for putting electrons in, you get to the point at the end where you have 2 electrons left and 2 orbitals to put them in. So the rules say when you have 2 electrons and 2 orbitals of equal energy, 1 electron goes into each orbital. Right? So if you've got a bunch of people moving into an apartment complex and there's 2 apartments left and 2 people, chances are they're going to want to live in separate apartments. No? Okay. I mean, if it's your significant other or something like that, maybe. But maybe that metaphor doesn't work. But oxygen, because of the quantum mechanics, is a diradical. Now, we know that radicals do stuff. And you're breathing in radicals into your biological system, which is full of all sorts of functional groups and hydrogens that can be abstracted and so on and so forth. Is this an issue? Well, common sense says it's not. We've been oxygen-breathing organisms for how many years? I don't know the exact number, but it's a number with a lot of zeros on the end. Right? We haven't air-breathing mammals have been around for, 60 million years now. So probably breathing oxygen isn't the end of us. But other things can happen which can be bad. So it's not the O2 itself that's necessarily a problem, it's the other thing. So let's start by talking about oxygen itself. Oxygen itself is less reactive than a lot of other radicals because, simply put, these 2 unpaired electrons talk to each other. Now, they're having a long-distance relationship. It's not like they're paired together and they're spinning in opposite direction and making a pi bond and you're really happy. They're on opposite coasts. Right? One's on the left side, one's on the right side, and they do talk to each other, but you probably know how well long distance, how well long-distance relationships work, right? As long as there's nothing better presented to you at the time, you go with what you got. I'm not saying that I know that. Maybe you do. That was harsh? What? It was a bad metaphor? You didn't like that one? It was kind of mean. I'm sorry if you're in a long-distance relationship. I wasn't meaning to imply anything. How many of you are in long-distance relationships? Of course, you can't afford it these days, right? See, so how would you know what I'm talking about? Why is it harsh? Nobody knows what I'm talking about. All right, anyways. The issue is when oxygen gets inside you. So if you get oxygen into, let's say, your mitochondria, where there's lots of electron transfer processes going on, that electron transfer, that electron that's being transferred, may leak out of that process and end up going to the oxygen. Now, the oxygen has 2 unpaired electrons, and here's this extra electron floating around. What do you think happens? Electrons like to be paired. Right? It's like if you're having that long-distance relationship and it's not working out for you, and something else happens to come along that's in the same city as you, you might be distracted. Or is that too harsh? All right. Anyway, so the oxygen can pick up an electron. So now on one of the oxygens, it has a full octet. All electrons are paired, 3 lone pairs, 1 sigma bond. We end up with a formal negative charge. The other oxygen atom now has that 1 unpaired electron. Now, the problem with that is because the oxygen that's paired up is no longer talking to the oxygen that's not paired up. So if you have that long-distance relationship, and one person's in LA and the other one's in New York, and the person in New York hooks up, the person in LA feels a little lonely, right? They may become a little more desperate, a little more reactive to do their own thing. Same thing happens here. So this structure, which is called superoxide, you can imagine, this thing flying around with a big S on its chest, superoxide. Bree, how come nobody ever laughs at that joke, huh? I said it too much, okay. So I have to have new jokes all the time? Is that it? All right. Well, we have budget cuts. I don't have writers, so what can I say? Me and Jay Leno work together that way. All right, anyway, so the superoxide is more reactive than oxygen, and it is something that's floating around, and it can do damage. It can do the kinds of things that radicals do, and we'll talk about that in a second. But the good news with superoxide is there are things out there, enzymes, whose job it is to seek out and destroy superoxide, like the Luthlexor enzyme, I guess. I don't know. But its job is to go and destroy superoxide to prevent it from being a problem. But if they don't get to it, then the superoxide can pick up a proton from somewhere. After all, it's an O- without any special stabilization, so it's a pretty strong base. It can get protonated, pick up another hydrogen atom from taking it from somewhere in its environment, and that makes hydrogen peroxide, which, as we've seen, can come apart, and you end up with a hydroxyl radical. That is the real bad guy. Hydroxyl radical, very aggressive. And then that can do all sorts of bad things. Now, here's the problem, is this happens right within the cell, maybe even right in the mitochondria. So basically, you're generating lethal weapons right inside the mitochondria. And how do you think the mitochondria feels with a hydroxyl radical floating around damaging things? Not too well. So this kind of process happens. As a matter of fact, some organisms deliberately make things like superoxide to use to attack other organisms that invade them. I don't think human beings do that, but some other organisms do. So there's got to be some protection for this. I mean, it can lead to damage. Let's talk about the damage. Let's talk about the protection. The damage kind of things it can do is this. For example, imagine this hydroxyl radical gets generated in the middle of or around the phospholipid bilayer, cell membranes. I think mitochondria have their own phospholipid bilayer that separates them from their environment, their own exclusive little club. This thing is full of, among other things, fatty acid side chains that have carbon-carbon double bonds in them. And next to carbon-carbon double bonds are often hydrogens that can be removed by hydroxyl radical, because the radical that's left over, when this OH dot takes away that hydrogen, this radical that's left over has nice resonance stabilization. A lot of polyunsaturated fatty acids have two alkenes that are not conjugated, so it's alkene CH2 alkene, and the hydrogens between the two alkenes are especially susceptible to this because they have really nice resonance stabilization. Otherwise, they're easy to remove. So what happens when you get a radical? Well, it can add to a pi bond, it can do atom transfer, or it can do radical combination. If you've generated this radical in the vicinity of other unsaturated side chains, this radical can add to that alkene, which makes a new radical, but importantly, makes this carbon-carbon bond. Now, what you've done here is you've taken two fatty acid side chains, and you've covalently linked them together. Now, what that means is your membrane can no longer be as flexible as it needs to be. The phospholipid bilayer's flexibility comes from the fact that the things that make it up are non-covalently associated. Now you've glued them to each other. Imagine you will, this is a brand new metaphor, let's see if this works. Let's imagine we're all fatty acids. We're all phospholipids. Together we're going to form one big membrane, right? We're flowing, moving around, we're flexible, there's proteins going in and out, we're transporting potassium cations, we're doing all that other kind of stuff. Oh, we have to move in our environment, so we change our shape. Everything's cool. Now form a covalent bond to your neighbor. Go ahead, form a covalent bond. Here comes a hydroxide. Psst, everybody's forming covalent bonds. Make covalent bonds. Nobody wants to make covalent bonds. All right, imagine you've done as I've asked and you've made covalent bonds, and now you're trying to do this, be a flexible membrane anymore, because you are covalently bonded to your neighbor, you're not as flexible. It's harder for things to move in and out, etc. In other words, you've damaged the membrane. And you can do a lot of damage to the membrane because this radical process is a chain process. It only takes one hydroxyl to make a whole lot of carbon-carbon bonds. So that's why chain processes can be pretty insidious, bad, however you'd like to say it. Now, what does this lead to? Among other things, with cell membranes, it leads to lack of flexibility. We've talked about that. It can also lead to reduced solubility. If you have free-floating fatty acids or fatty acid-derived lipids in the bloodstream and they become bonded to each other, they become much less soluble. And what happens when lipids that become bonded to each other and therefore are not soluble deposit out in places like arteries, arteriosclerosis? So there are arguments that plaque in your arteries potentially comes from free radical processes. Now, we couldn't have survive this long as mammals if oxygen was going to be this much of a problem. We didn't get rid of the oxygen, obviously. We have defense against it. Now, there's many, many kinds of defenses. One of them is, as I mentioned, a group of enzymes called superoxide dismutase, whose job it is to chew up superoxide. They basically convert superoxide into oxygen. Now, they may also make hydrogen peroxide, which is a whole other issue, but I think it gets disposed of in a different way. There are non-enzymatic defenses as well, and to think about where they come from, let's think about why is that phospholipid side chain susceptible to hydroxyl radical attack. So if you go back to the previous slide, previous page, 43, what is it that makes What is it about the structure of this molecule, the alkene, that makes this process easy? You say it every other time, and I don't want you to. Resonance, right? The product you get out of this is a highly resonance stabilized radical, easy to make. So what you do, if you want to get the hydroxyl radical, you want to distract it, you go, hey, hydroxyl radical, ignore the superacid or ignore the fatty acid chain, react with me. I'm more interesting. I'm easier to react with. So in other words, the things that you're going to put in there to kind of to sacrifice themselves to the hydroxyl radical, they're susceptible because of this resonance we talked about. So we want an efficient antioxidant, a thing that's going to protect against hydroxyl radical. It's something that's going to sacrifice itself to hydroxyl radical. We're going to give it even better resonance. So a lot, not all, but many of the naturally occurring antioxidants are molecules such that when you take a hydrogen away, the radical you end up with has really nice resonance. So what we want here is lots of resonance, because having lots of resonance contributors reduces, not only does it make this hydrogen easier to remove, but once we've made this radical, it's less reactive, and so the chain won't propagate as quickly. So the antioxidants actually don't serve to terminate the radical chain. They still allow it to propagate, but once the chain propagates, once they come to the next step, the radicals that are produced are so unreactive that they just don't move forward. All right. So here are some kinds of antioxidants. Now, generally, because we have to protect against radicals in both fatty tissues and non-fatty tissues, we have two categories. We have the lipophilic, those are the hydrophobic antioxidants. These are the ones that like to dissolve and like to hang around in fatty tissues. And these are things which tend to be more nonpolar in their nature. Vitamin E is probably the most well-known of these. Here's vitamin E. And vitamin E is actually a mixture of things. Alpha-tocopherol is the most important component. And you can see it's got a whole bunch of hydrocarbon to it. It's got very little polarity. It's got an OH bond up here, and it's got some CO bonds down there. But the vast majority of that is CC and CH bonds. So very nonpolar molecule that likes to hang around in nonpolar tissues. What in this particular molecule, what hydrogen gets abstracted by the radicals that it's trying to protect against? Right here. It's the OH. And I'll leave it to you as an exercise to draw that set of curved arrows and what the radical that's produced from that would look like. Carotenes also serve antioxidant functions as well as coenzyme Q, although coenzyme Q, I think, works by an electron transfer process, not a hydrogen abstraction process. And then on the next page, of course, we have antioxidants which we need for lipophobic circumstances, hydrophilic, things which like to dissolve in more polar tissues, in water and so forth. Ascorbate, vitamin C is by far the most well-known of those. And as it turns out, it is this hydrogen, again, it's the OH hydrogen that is abstracted by the radical. Now, you might think it's this hydrogen up here, the one on the CH bond that's next to the ester. Turns out that's not the one. To tell you the truth, I'm not completely sure why it is, but that turns out to be the case. And uric acid also is an antioxidant, but it doesn't work by that same way. Now, let me give you another metaphor to think about the way the antioxidants work. And maybe this metaphor doesn't work around here, UCLA, so well in the past year or two. The antioxidants are like the blockers on the football team. The guy who carries the ball, that's the important guy. That's who you might want to protect. So that guy you're protecting in biological terms might be the membrane. It might be DNA, because you don't want to damage DNA. It might be RNA. It might be a huge number of things. So that's what you want to protect. So the job of the blocker on the football team is to get in front of the guy that's carrying the football and deliberately sacrifice himself to the opponents. So that's what the antioxidants do. Their job is to get in front of whatever they're protecting and to say, hey, react with me. You want to react with me. I'm better to react with. Ignore the DNA. React with me. All right, the next radical topic we're going to talk about, I don't think we're going to have time to start on today, so I will leave it to you to think, maybe even want to research this topic. There's an awful amount of information out there on the internet. We're going to talk about CFCs and ozone depletion. In other words, the legacy of my generation to yours. Remember, we're closed on Monday, so we'll see you on Wednesday.